Okay, continuing along, let's talk about space quantization and the vector model. So this is going to synthesize all of this stuff we've been talking about with vectors. Okay, so first let's kind of recover some of the information that we have already. So summarizing what we learned from the particle on a ring, we got our wave function. We have our angular momentum operator in the z dimension. Notably, in the z dimension, it's only dependent upon angle phi. And if you recall, when we operated on that particle on a ring, we got ml h bar times psi. So the magnitude of our angular momentum is given by ml h bar. And now we can specifically say that's the magnitude on the z-axis, right? So when ml is taking on positive values, that's corresponding to rotation in this orientation. And when ml takes on negative values, that corresponds to rotation and this dimension. So what about those values in between, right, where we let theta pitch in and out of the yz or xz plane? So now we can start to compare our particle on a ring result to our particle on a sphere result. So in the particle on a ring, the energy solution was ml squared h bar squared over 2 times I, and the projected z component of angular momentum is given by ml h bar. So we can draw some parallels to that for the particle on a sphere result. So we didn't talk about this energy solution before, or at least not in much detail. But the energy solution for particle on a sphere is given by L times L plus 1 times h bar squared over 2 times I. So noting the parallels there that we see with the particle on a ring result, we now can get the total magnitude of our angular momentum in all dimensions as root L times L plus 1 times the quantity h bar. So now when we start to create this picture, we can make something that looks like this, remembering that our coordinate system has z pointing up, and the x and y are arbitrary from there. So we can see that the ml h bar is the projected z component on angular momentum. But now our total magnitude is given by this quantity. So when we see this angle here being created, which we can simply compute with SOHCAHTOA, so the cosine of that angle theta will be given as ml over root L times L plus 1. So now when we ask the question, well, which way is this particle rotating? Well, based on this being the total magnitude, right, then we can say that the rotational axis is normal to that vector. So in this case, our particle looks like it's pitched somewhere out in that theta dimension. Its overall magnitude is pointing where my thumb is, but now you can see in this vector, it will have projected length on to the z-axis, right? And so I guess technically, I drew that arrow pointing this way, right? But if we recall from our vector addition, if I added this z component to this horizontal component, I would end up with my total vector and its magnitude. So now we can begin to appreciate what's going to happen to our particle as we pitch it in and out of our theta dimension. We can also create a set of these degenerate states with the various L and ML values and their respective angular momentum on the z-axis. So that will be given as ML plus or minus h bar. And so you can see the following results occur right there. And if we now look at how all of these combine, we can make the following pictures. So suppose for now that L is equal to 2. So we know we're going to have -2, -1, 0, +1, +2 values of ml. So we're going to get 5 degenerate states. Well, here they are. And we can also begin to start specifying their various vector components. So if we start from the simple case of ml equals 0, which we discussed already, and just noting once again, our z component is pointing up. So then recall when we have ml equals 0, it's not rotating in the phi plane at all, rather entirely in the theta plane, which would give us 0 magnitude on the z-axis, but we still have angular momentum overall given to us by root L times L plus 1 h bar. So now for the case of L is equal to 2, that's going to go 2 plus 1 times 2 is 6, all square root. So the length of that vector will be root 6 h bar. Okay, so what happens now to the ml plus or minus 1? Well, as we can start to appreciate now, for the ml plus 1 state, we are going to have projected magnitude on the z-axis. That is going to be given as h bar, just 1 times h bar. So the length of that vector is h bar. And now correspondingly, the length of our total magnitude must still be root 6 h bar, We're not changing the value of L, okay? So then what's changing, obviously, is that angle theta and the way that we're pitching in and out of that dimension. So you can see for the ml minus 1 state, we've got projected magnitude on the z-axis of negative h bar. The length of our line here is still given as root 6 h bar. Lovely. And so now that angle theta has flipped over, So, and we can see the same case for ml2 and ml minus 2. So for ml plus 2, the length of this line must be 2 h bar. For ml minus 2, the length of this line must be minus 2 h bar. And the length of our overall magnitude is still given as root 6 h bar. So what do we learn from this? Well, if you recall that our angle phi is uncertain with respect to jz. So that means our particle could be found indefinitely anywhere along that angle phi. So based on this, we can kind of start to create these pictures, these cones of quantized area where we might expect to find the particle. You can see here that those are given by the exact angles that we would predict from our cosine of theta equals ml over root L times L plus 1. So this is all pretty cool. It's a little weird, but it shows us that the angular momentum of our particle is non-trivial. And when we start to think about the effects of this, we're going to see this come back in spectroscopy. So we have to consider the angular momentum of our electron as it's rotating around our nuclei, as it's undergoing spectroscopic transitions. So more on this vector model to come as we get into spectroscopy. Okay, I'll see you in the next video.